Hi everybody, welcome to the second half of 6.1 through 6.2. So these are more ways to approximate the area under a curve. We're going to go over midpoint sum and trapezoid sum, and both of those names should be hints of the process that we're about to use. So example 1 says approximate the area using the midpoint Riemann sum. Approximate the area under the curve for the function f of x equals 1 over x on the interval 1, 3 using midpoints of 4 subintervals of equal length. So to start off with, I'm going to draw a sketch of this graph. So the last couple problems, the graph has been provided to us. Today it's not, but that's okay. I'm going to do a sketch. I'm only going to give us, actually I'll just give us the whole quadrant, but we only need this half because it's 1 to 3. And I'll show you on Desmos what the graph looks like real quick, but it's like 1 over x. So I'm just going to draw like a little sketch of it. So I really just need like that section over there on the right between 1 and 3. So my picture as I draw it is just going to look like this, just so I kind of have an idea of what it looks like. And so I want to draw this from 1 to 3, and I'm really just going to use this to like help us with the concept. And so we want 4 equal subintervals again. So we want 4 subintervals. And then they need to be equal length. So what I need to start off doing is figure out what is the width of these 4 rectangles that I'm about to draw. So I'll do 4 subintervals. So I'm going to divide by 4, and then we're going from 1 to 3. So 3 minus 1, and so that will give us 2 over 4. So they'll be 1/2. So just like yesterday, all of our rectangles were 1/2 yesterday. Today they'll be 1/2 again. So if I go down here, I'm going to have to write pretty small. I'm basically going to make 4 rectangles. So 1, 2, 3, 4. And then this is 1.5, 2, 2.5, 3. And I'm not going to mark those right now. You'll see why, because it is with the midpoint. And I don't want to add too much to the graph. But the way that the midpoint works is instead of like the right Riemann sum creating the rectangle by pulling up from the right, or the left pulling up from the left, right? This is what we were doing. You're actually going to pull up from the middle of each function. And so each like width interval. And so this one is like a lot more accurate. You'll see when we draw these rectangles that they hold the curve a lot better than the left Riemann sum and the right Riemann sum, but they're a little bit more tedious. And so like that's kind of why you wouldn't want to use them. So for example, here's my first rectangle. The midpoint is like the middle point of the width. So I'll make a mark right here. And then I will pull up from the middle, and then I will make my rectangle that way. So this is what my rectangle is going to end up looking like that. And then this point right here is f of, so this would be f of 1.5, f of 2, f of 2.5. So this is actually f of 1.25. I'll do it again. I'm going to use a different color. So I'm taking this rectangle right here. I'm finding its midpoint, which is here. And then I'm creating my little rectangle, and this point right here that represents the height of my rectangle is f of 1.75. So this is what I mean by like all of these numbers are really weird, right? So I'm getting that because this is 2.5, this is 1.75. Continuing on, next rectangle, this is f of 2.25 because 2.25, and then finally this last rectangle, and that is being made using f of 2.75. So really, like what I just want you to see based on yesterday is there's not that much like space that's not used, right? Between 1 and 3, like this space gets left out, this space gets left out, and this space gets left out, but then we have this space that hovers over it. So in some ways it kind of cancels it out. So this approximation looks like pretty accurate to me. And so now we're actually going to like evaluate. So we drew a picture just to kind of help us with the concept, but now we'll evaluate. So if I go here, this is my integral. Remember, my integral is the symbol we use to like abbreviate the phrase area under the curve. So I'm trying to find the area under the curve from 1 to 3 of 1 over x dx, and I'm going to approximate it. So I have 4 rectangles again, so I should have like, when I find the area of all these rectangles, I should have 4 area statements. So the first area, the width is 1/2, and remember we used this line right here to create our height, and that's f of 1.25. So I'm going to do f of 1.25, and then again 1/2 f of 1.75 plus 1/2 f of 2.25 plus 1/2 f of 2.75. Okay? So now I'm just gonna, keep going. The widths are all the same, so I'm just gonna factor out the 1/2. And then to actually find these heights, I'll use the equation of the curve to figure out the heights. And so the equation of the curve is 1/2. So it'll be like it's 1 over x. So then it'll be 1 over 1.25, 1 over 1.75, 1 over 2.25, and 1 over 2.75. And just for the sake of time, feel free to do that yourself. Check my work, see if I'm correct, but it should be 1.09 units. And then we're going to be squared unless they give us like units or something like that. Okay, take a second, process that. Okay, next problem. So now, that was the midpoint. The next one's the trapezoid one, which the trapezoid one, I feel like of all approximations is really the most accurate. But the problem is you have to find the area of a trapezoid, so you might not prefer it. Okay, so approximate the area under the curve of the function, so it should be f of x equals the square root of x minus 1 on the interval with 5 subintervals, on the interval, 1, 6, with 5 equal subintervals using a trapezoidal Riemann sum. So I'm going to start by drawing the pictures, and then we'll kind of talk about the big idea here. So for this one, we want 5 equal subintervals from 1 to 6. So this is going to be nice because that means that each subinterval is going to have a width of 1. So that helps us out a lot. So I'm going to go ahead and draw the picture. So I'm basically going to have 1, 2, 3, 4, 5, 6 trapezoids. So I'm just going to make marks like where the different trapezoids are going to be here. I had some marks left over from last year. And now what I'm going to do is I'm going to draw trapezoids. So I'm going to kind of pull up from each point and add a point just to help guide me. And I'm going to have 1, 2, 3, 4, 5, 6 trapezoids. So some of them aren't going to look like a trapezoid. For example, this first one, if I connect all these points, that looks more like a triangle. But that's just because this point, if I were to try to go parallel to it, it's just it won't go up. There's no more curve. But then this next one, this makes a trapezoid. And if you're like, those don't look like trapezoids, just turn your paper and they will look like trapezoids. So I have 6 trapezoids now. And as you get the hang of this, you can do these problems without taking a picture as you get the hang of them. So those are the trapezoids, and now we're going to use those to help us approximate the curve. Real quick, I'm going to go through and label some of these, though, because basically, I'll actually write it out first. Okay, so I'm going to say I'm trying to find the area under the curve of the square root of x minus 1 dx from 1 to 6. And so now there are 6 trapezoids, so I'm going to find 6 trapezoid areas. The trapezoid area formula, which is what you'll have to use, is base 1 plus base 2 divided by 2 times h. The other day in class, I think I told you, take your trapezoid and split it into triangles and rectangles. That will take you way too long if you do this one. And so you need to use this formula over here. Now, let's just talk real quick about, in this picture, what is what. So I'm going to come over here to this trapezoid right here. So the bases of a trapezoid are the sides that are parallel to each other. So if you guys look here, this has a slant and this doesn't. So these aren't the bases, okay? And that's why you might need to rotate your paper to actually envision a trapezoid here. But the bases here is this one and this one right here. So this is B1 and this is B2. And then the height of a trapezoid is the length that runs perpendicular to the bases. So this is the height right here. Height. So let's keep that in mind as we write the areas of all these. So we're going to start over here with this first one. This one is literally a triangle, so we don't need to use the trapezoid formula for this. It's 2 times f of 2, and we'll figure out what f of 2 is in a little bit. We're just setting it up right now. So say we want to use the trapezoid formula for here. There's only one base, so you put 0 for one of the bases. You would put f of 2 for the other base. You would divide by 2, and then the height, which is like the width in this problem, is 1. Yeah, okay, cool. So that's the first one, okay? So that was our first one. Next, we'll do this next one. And so for this one, we have f of 2 as one of the base heights, and then the other base height is f of 3. And then based on the trapezoid formula, you would add those together, divide by 2, and times by your height, which is 1. Okay, and then I'm just going to repeat this process. So f of 4 goes here, f of 5 goes here, f of 6 goes here, and f of 7. So when I'm done with this, I should have 6 trapezoid formulas. So right now I have 2, and so I need 4 more. So feel free to write these out and try your best with them, but the next one will be f of 3 plus f of 4 times 1 over 2. And then it'll be f of 4 plus f of 5 divided by 2 times 1. And then I'll just keep going. Notice that each one besides the first one, which didn't exist, repeats. Like each base repeats, because each base so far has been used in 2 trapezoids, except for this one that won't happen to, and this won't happen to. But every other one is used in twice, and so you'll kind of get a pattern there that you'll eventually be able to use, say, if you don't want to draw a picture. And then this last one, so f of 7 isn't used twice because f of 7 is only used in this last one, versus like 6 was used in this one and this one, f of 5 was used in this one and this one, you know, so on. So that got really big. So now we're just going to go ahead and simplify. So one term that is in all of these 1, 2, 3, 4, 5, 6 is the division by 2 and the multiplication by 1. And so I'm going to go ahead, as I try to simplify this expression, I am going to factor out a 1/2. And then what would be left in the first expression is just f of 2. I don't have to write 0. What would be left in this expression is f of 2 plus f of 3, and then f of 3 plus f of 4. So I'm going to just like color code the first two so you know like the connection between. I won't do them for all. But like this comes from that first area formula. This comes from the second area formula. This comes from the third area formula. So on and so on. And then we got this. And then one more thing you could do to simplify is, if you notice, which I already mentioned this, we're running out of space here, so I'm sorry. Every single term besides this last one is used twice, right? Twice, 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 twice. So I can just go ahead, so I don't have to like do so much addition. I can write 2 of f of 2, 2 of f of 3, 2 of f of 4, 2 of f of 5, 2 of f of 6, and then 1 of f of 7, and that will make my evaluation step a little bit easier. So from here, now I just have to plug in to this curves equation to find all of these values. And that curves equation is the square root of x minus 1. So for this one, I'll have 2 times 2 minus 1, which is 1. And then I'll have 2 times 3 minus 1, which is 2. So I'm just plugging in here, and I'm subtracting 1 before I even put it in the inequality. Or, sorry, the inequality, the rational function. And this last one, I'm not putting a 2 with it because there's only 1. And so that's kind of all the work. You would type that all into your calculator. If you have any questions, like from here, like these steps, this is like the setting up the areas, and then I'm simplifying here, and I'm simplifying here, and then here I'm using the curve equation to find the heights of all these trapezoids, or sorry, the base of all these trapezoids. Yeah. And so when you put this in the calculator, you should be getting out 7.26 units squared. Okay, we're going to do one more. Example 3 and 4 are the same question, just twice. So for this one, it says approximate the area under using the trapezoid Riemann sum. G of x is a continuous function from 0 to 25, where g of x is the rate that Catherine travels from home to school. G of x is in miles per minute and x is in minutes. Let's find the distance that Catherine travels. Find the distance using a trapezoidal Riemann sum. So when you get the hang of this, you're not always going to have to draw a picture. Like, I could probably solve this without drawing a picture. But today we're going to. And then, again, as you memorize the process more, you won't. But one thing I want you guys to notice with this one is these are not equal subintervals anymore. Okay, so the evaluation will be a little bit trickier. There's a distance of 2 here, 4 here, 2 here, 7, 5, and 5. I'm actually going to go ahead and write those out because we're going to need those, because those are going to represent the height, or the width of our trapezoid. But just to help us out with this one, I'm going to do a little sketch over here on the side, and we got to go up to 25, so I'm going to count by 5s. This is for the x. That was not counting by 5s. I'm very sorry. Okay, so this is x, and then this is g of x over here, and I'm going to count by 5s there too. Okay, this is g of x. So, g of x, I'm going to see if I can scoot this over a little bit. So that's our graph. So I'm just going to plot these points briefly. So 0, 2 is here. Oh, sorry, 0, 10 goes right here. 2, 14, 6, 20, 8, 15, 15, 30, 20, 20, and then 25, 10. Okay, so those are those plots, and I'll go ahead and connect them like that. Now, it wants us to have, actually doesn't tell us how many subintervals we're going to have, so we're just going to do the intervals where the different points are. So I'm going to go ahead and draw some trapezoids now. So my first trapezoid is going to be this one, and then this one, and then here, 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 and then here. So notice a lot of trapezoids are bigger than others, but we just have to use the intervals that we're given, or else we won't have anything else to go off of. So from here, I'm going to go ahead and approximate. Now that I have my picture, I've really set a lot of things up for myself. So I'm trying to find, also this connects to what we were doing the other day. So it says trapezoidal Riemann sum, so you know that you should do this. But if you find the area under the curve of a rate function, you will get, so if the rate is miles per minute, you will figure out, if you take the area under that curve, you'll figure out the accumulation of miles. Or like the other day we were working on the snow. And so since we found the area under the curve of the function that was snow per minute, then we found the accumulation of the snow. Or velocity is like distance over time. And so we figured out the total distance that squirrel had traveled. So that's why we're doing what we're doing, but it also tells us to do the trapezoidal Riemann sum. So it gives us like a huge hint. But that's like the concept behind this. So now I'm going to approximate, and then I'm just going to find the area of all of my different trapezoids. So this first trapezoid, if I go back here, this tells me that the width is 2. But first, this height, this base is 10, and then this base is 14. The reason I'm using these as the bases is because they're the sides in the trapezoid that are parallel to each other. So the trapezoid equation, I'm going to do base plus base divided by 2 times the height. In this case, it's 2. So that is this first one. The next one, the bases, and I'm using my table to find these. So the bases were 14 and 20. So it'll be 14 plus 20 over 2, and then this height was 4. So that's that. Continuing on, when I'm done, I should have 1, 2, 3, 4, 5, 6 area formulas. So the next section was 20 and 15 all over 2 times 2. So that was this one. And feel free to write these out if you feel like you got them. You don't have to wait around for me. Next one is 15 and 30. Divide by 2 because that's the trapezoid formula. And then the height was 7. I'm getting that from my table. Next is going to be 30 plus 20 all over 2 times 5. And that is this guy. And then the one more, because I have 6, it's going to be 20 plus 10 over 2 times 5. And that is this one. So now I just got to evaluate. So not all of them have the same width, but they all are being divided by 2. Sorry. So I can pull out the 1/2 from all of them, so I don't have to deal with the division by 2 anymore. And then if I pull out the 1/2, I'm going to do some work in my head, but I'm basically going to be, like, this is going to be gone. So you'd have 10 plus 14 that you have to do first, because they're, like, in parentheses, imaginary ones, but this would be 24 times 2, so that's 48. This is going to be 34 times 4, and that is 136. I didn't do that in my head. I looked at my notes from last year. 35 times 2 is 70. 45 times 7 is 315. 30 plus 20 is 50 times 5 is 250. And then 30 times 5 is 150. And then I'll put all of this in my calculator. You get 969 out. And then if you divide that by 2, you get 484.5. And then the answer is miles. That is the distance she travels from her home to school. So those are the notes today. Hope you had fun. Hope you enjoyed. And email me with any questions.